So when I asked for student feedback on a video topic, the overwhelming majority wanted something on Markov chains. So I've made a short little video talking a bit about Markov chains. So I'm going to share my screen with you. If I can get to it. Here we go. All right. So let's think about spreading of a virus in a population of 1,000 mice. So we're going to say, suppose we have a closed population of 1,000 mice, closed in that no mice leave the population, no mice enter the population. Okay. And so during 1 week, there's an 80% chance that an infected mouse will become non-infected. And of course, that means that there's a 20% chance that an infected mouse will stay infected. And then there's a 30% chance that a non-infected mouse will become infected. Likewise, that means that there's a 70% chance that a non-infected mouse will stay non-infected. All right, and so one task that we have, we're going to draw a Markov chain diagram. We're going to construct a stochastic matrix of transition probabilities. And then we're going to answer some questions. It says if we currently have 400 infected mice and 600 non-infected mice, then what will the population look like in 1 week, in 2 weeks, and then in the long term? What's going to happen? Okay, so I've got a little crude diagram here that I've made. Okay, so we've got I for the infected state, N for the non-infected state. And as the problem mentioned, during 1 week, there is an 80% chance that we're going to transition, that an infected mouse will transition to being non-infected. And of course, then there's a 20% chance that that infected mouse will stay infected. And then it says there's a 30% chance that we are going to have a non-infected mouse transition to being infected. And of course, a 70% chance that that non-infected mouse will stay non-infected. All right, so there's our diagram. It basically looks at all the different ways we can transition from one state to another. So again, it's a simple two-state Markov chain. All right, now we're going to convert this into a probability matrix. So in a probability matrix, in our stochastic matrix, the columns are going to be adding up to 1. And so we're going to think about column 1 being starting out in the infected state. And then column 2 will be starting out in the non-infected state. Row 1 will be transitioning to the infected state. And then row 2 will be transitioning to the non-infected state. All right. So again, if we go to the next slide, okay, so here's our point 2, that's infected, staying infected. And then point 8 is the infected becoming non-infected. Point 3, well, that was the non-infected becoming infected. And then point 7, that's non-infected, but then staying non-infected. Okay, so again, each of the columns is kind of like where we are now. The rows are where we're going in the next step. And then we have what's called a state matrix. In other words, what's the situation now? All right. So the situation now, we're saying if we currently have 400 infected mice and 600 non-infected mice. Again, I made, that first column, first row being about infected. So So 400 infected, that's the first entry. 600 non-infected, that's the second entry. All right. And so the way we've set up the transition matrix here, excuse me, again, having the columns adding up to 1 and going, from and then to, that's set up to have your matrix, your transition matrix being multiplied by the state matrix. In other words, having the state matrix on the right side as a column. All right. There's other ways of doing this. Our textbook and all the stuff that I'm telling you this is how we're going to do it. All right. There's another way of doing it, and you're multiplying on the left by a row state matrix. I don't want y'all to do that because, again, it can get very confusing if we have like all these different ways of doing it. So I'm saying do it this way. In fact, on the lab, I'm saying if you do it a different way, you get a 0. All right, because typically that means, you talk to somebody else and had somebody else do it for you. All right, so this is how I want y'all to do it. Okay, so anyway, after 1 week, we want to know, well, what's going to happen after 1 week? We're going to multiply the transition matrix times our state matrix. And we're going to wind up with 260 and 740. All right, we just do matrix multiplication. You can throw it into a calculator if you want to, but you could probably work this out by hand. And so doing that, again, we get 260 and 740, which means that after 1 week, again, we had 400 infected. Now it's dropped down to 260. And we have 740 now that are non-infected, which makes a bit of sense because we see that, there was a great percentage that were going to transition from being infected to non-infected, and not that great a percentage that are going to become infected. Now, one thing about this is that it doesn't prevent mice that went from infected to non-infected. They can still become infected again. Okay, so we haven't made that idea of, once they're recovered, they're never going to get infected again. That would make us have like another state. So that would get a little bit more complicated. All right, but anyway, so then the question is, well, what's going to happen after 2 weeks? So what we can do is simply just take our transition matrix to the second power and then multiply it times our initial state matrix. When we do that, we get this 274 and 726. And again, this is something that you can do in your calculators. Online, Symbolab is kind of nice when it comes to matrix multiplication. So that's one tool you can use, especially when you get into larger matrices. So anyway, we multiply this out and we get 274 and 726, which means after 2 weeks, we're going to have 274 infected mice and 726 non-infected mice. So the infection is starting to creep back up again. So it's like, okay, well, what's going to happen? What's going to happen in the long term? Well, one of the things about this particular example is this is an example of a regular Markov chain. All right. So in other words, we don't have rows or columns heading to 0. All right. So, and again, you can go back and look at the precise definition for regular matrix. But anyway, this is a regular matrix. And I say this because in a regular matrix, the long-term sort of outcome is the steady state solution. So there were a number of people asking about how we determine a steady state solution, and it's pretty simple. It is pretty simple. So the idea, we're going to call this steady state solution X bar. Some vector. We don't know what the components are, but we do know that we want the result to be that steady state matrix. So I want to have my transition matrix times X bar. That's going to equal X bar. Okay, kind of an odd equation to solve here. Now we got to remember we're dealing with matrix algebra. And so that X bar we would like to think of that, using our sort of old sort of algebraic ideas as 1x bar. But we know that in matrix multiplication, there's no such thing as a one matrix. We have the identity matrix, I. And that identity matrix is ones along the main diagonal. That's the one that goes from top left to bottom right, and then 0 everywhere else. So there is our identity matrix. And so what we can do is we can subtract that identity matrix times x bar from both sides, because now I can just sort of factor out the x bar once that happens. And so we'll have 0.20, excuse me, minus 1. So it gives us a negative 0.80. And then 0.3 minus 0. Okay, that's 0.3. That's easy enough. 0.80 minus 0, 0.80, great. And then 0.7 minus 1, well, that's negative 0.30. Oh, okay, well, that looks rather interesting. It also looks like we've got a dependent system. That's typically going to happen here. All right, we'll have a dependent system. And so to solve, we can we put this matrix into reduced echelon form, and it turns out we get 1 and then negative 0.375. And of course, 0 is on the bottom there. And so because column 2 did not have a leading 1, we'll let that be our parameter. We'll let x2 equal t. And so therefore x1, working that out, would have to be 0.375 times t. Right? Again, we plop those back in, we see that, yeah, that's going to give us 0. Now, the one thing to note, you look at this going, wait a minute, I'm supposed to get a single solution out of this, and we got this infinite amount of solutions here. Yeah, but there's one extra thing that we've got. We know that we're going to have 1,000 mice. So we know that the sum of these two values is going to equal 1,000. And so that leads us to, hey, now I can get a value for t. And so we get 727.2727. It repeats. And so we'll round it to the nearest mouse. Okay, that came out wrong. But anyway, so we get 727 non-infected mice. And then we'll have 273 that are infected. That's sort of the long-term solution. Now, that doesn't mean that it's going to be the same 727 mice that are non-infected. It doesn't mean that, okay, we've got these great mice that are totally immune and we got these poor 273, sort of like decrepit, constantly infected mice. No. It just means that, when, we get the sort of cycle of, okay, we got some that are becoming non-infected and we got others that are being infected, but we're going to have, in the long run, it's going to balance out to be in about roughly 72.7% are going to be non-infected and 27.3% are going to be infected. Okay. Again, if the players are going to change up, okay, this mouse is now infected. Okay, poor mouse. Oh, this one's, done well, receiving get well soon cards, etc. But anyway, so you get the idea. All righty. So again, that's the idea of a steady state solution. In the project, we've got some absorbing states and we've got some reflecting states, and that is part of the idea of a non-regular Markov chain. And so I'll have some other videos that are going to talk about that. All right. Well, I hope this helped out. Again, keep sending me questions.